welcome back. In this video, we're going to be comparing means, which is not very dissimilar to other hypothesis tests that we have done so far. So if you'll remember, the population model parameter of interest is going to be the difference between the two means. Just like when we were comparing two proportions, it was the difference between the two population proportions. So here we're looking at mu1 minus mu2. Mu1 is just the mean of the population of your first set of data, and mu2 is the population of the mean for your second set of data. Of course, the statistic of interest is our sample statistic, which is the difference of the two observed means, which is going to be y bar 1, which is your sample mean from population 1, and we're going to subtract that. We're going to subtract y bar 2, which is your mean of your population from set 2. We're going to have to tweak our formula slightly since we're dealing with two samples. So to find the standard deviation of the difference between the two independent sample means, we of course add the variances and then take the square root. So we're going to be looking at sigma squared of your first set of data over the sample size for your first set of data plus sigma squared for your second data set divided by the sample size of your second data set. And of course, we're going to replace sigma 1 and sigma 2 with S1 and S2, which are your sample standard deviations, to calculate the standard error because we don't necessarily know the population standard deviations. We're going to, of course, look at confidence intervals in addition to hypothesis tests. So again, it's the same generic formula as before, where you're given your point estimate plus or minus your margin of error. So here you have your point estimate, which is just the difference of the two sample means. And then here you have your margin of error, which is your t critical value, which we determine again from your degrees of freedom. And then we multiply that by the standard error of the difference of the two means. Our degrees of freedom are going to change here since we're dealing with two samples. And the formula to calculate degrees of freedom is quite complicated, so we're not going to get into all of that. You can always confer with the textbook if you're interested in seeing that formula. You can also use technology to figure out the critical value. We're going to just simply take an estimate. So the best way to do that is just to add your two sample sizes and just subtract 2. And the 2 represents the two unknown parameters. So here we have our formula for calculating our t value, which is just, again, the value of our statistics, which is y bar 1 minus y bar 2. We're going to subtract mu1 minus mu2, which are our population means, and we're going to divide that by the standard error of the difference of the two means. And here is the standard error formula that we're going to use. Again, we don't know our population standard deviation, so instead we're going to use S, which is our sample standard deviations. Now, before you can calculate a two-sample t interval, which is going to be our confidence interval, or perform a two-sample t test, which is going to be our hypothesis test, you always want to check your assumptions and conditions. So you want to check the independent groups assumption, where you're just checking to make sure that the two groups we are comparing are independent of each other. And then the independence assumption is satisfied when you check randomization and the 10% condition, which we've seen in every test and confidence interval. And then we have the normal population assumption or the nearly normal condition. And if the sample size is less than 30 for each sample, then the data from the sample should be unimodal and reasonably symmetric. The larger the sample size, of course, the better. The shape of the distribution won't indicate trouble unless there's a severe deviation from normality. So if we had, some extreme skewness or something, even if the sample size was greater than or equal to 30, we want to be cautious using the t-model. Anytime we have these examples, please pause to read the problem, and then you can even attempt the problem on your own if you'd like, and then you can unpause when you're ready to go over it. Can you tell how much you are eating from how full you are, or do you need visual cues? Researchers constructed a table with two ordinary 18-ounce soup bowls and two identical-looking bowls that had been modified slowly, imperceptibly refill as they were emptied. They assigned experiment participants to the bowls randomly and served them tomato soup. Those eating from their ordinary bowls had their bowls refilled by ladle whenever they were 1/4 full. If people judge their portions by internal cues, they should eat about the same amount. The results are summarized in the table. So here we have 27 participants that had ordinary bowls and 27 that had the bowls that self-refilled. And then the mean amount of ounces for the ordinary bowl was 8.5 ounces, and the refilled bowl was 14.7 ounces. And then here we have our sample standard deviations of 6.1 and 8.4. So what does a 95% confidence interval say about the difference in mean amounts eaten? Assume the conditions for inference have been satisfied. So again, we would, say that the two samples are independent of each other, like the people eating out of the ordinary bowl would have no influence on the people that are eating from the refilled bowl. It does tell us that it was a random group of people, and we know that 27 in each group is less than 10% of the population of people, and we have 27 in each. We would assume that it would probably be unimodal and reasonably symmetric since they're less than 30. Okay, so we want to calculate a 95% confidence interval. And anytime you want to calculate a confidence interval, just remember your generic formula, which is your point estimate. So in this case, it's going to be my y bar, let's say O for ordinary. And then actually let's do refilled minus ordinary because I want to keep it positive. So my refilled is bigger than my ordinary. It doesn't matter, but your interpretation at the end would matter. So I'm just going to do R for refilled and then Y bar O for ordinary. So you have your sample mean amount for those that ate from the refilled bowls, and you're subtracting the sample mean of those who ate from the ordinary bowls. So that's my point estimate, and then it's plus or minus my margin of error, which is made up from my critical value. Okay, so in order to find that, I need the degrees of freedom, which remember is just going to be the sample size of each sample, and then we're going to subtract 2. So you get 52. So I'm going to be looking for T star with 52 degrees freedom. And then you have your standard error, which remember is just going to be the square root of the standard deviation of your first set, so the refilled squared, divided by the sample size of the refilled, plus the standard deviation of your second set squared, divided by the sample size of your second set. So I'm going to change that to a 1. And change that to a 2. Actually, let's keep it the same. Let me rewrite this so we're using the same letters to make it less confusing. Let's do refilled squared over the number of people in the refill group, and then plus the ordinary squared over the number of people in the ordinary group. Okay, this way it'll make it less confusing. All right, so now I'm just going to plug in my numbers. So I have 14.7 minus 8.5 plus or minus. We're going to find T star 52 here. So we're doing a 95% confidence interval. So I have to go to my T table. And I am dealing with 95% confidence. Okay, so I'm right here. And if I scroll down in that column, I want to go to degrees of freedom 54, and remember there is no 54, so you round down to 50. So my critical value would be 2.009. So this is going to be 2.009. So again, T star 52 is going to be the same as T star 50, which was 2.009. And we got that from the table. Okay, and then I'm going to plug in my numbers here. So I have 8.4 squared over 27 plus 6.1 squared over 27. And then it's the square root. Now, when I multiply all of this together, and when I subtract those two, I get 6.2 plus or minus. My margin of error is going to be about 4.0. And if I do 6.2 minus 4.0, I get 2.2. And 6.2 plus 4.0, I get 10.2. So there's my interval. Now our job is to interpret it. So let me shrink it so we have some room to write our interpretation. So of course we're going to start out saying, I am 95% confident that the people eating from the refill bowl will eat an average. And it's important to use that word because we're looking at the average amount eaten. We'll eat an average of between 2.2 ounces and 10.2 ounces more. Because remember, we're comparing two groups here. More than those eating from the ordinary bowls. So remember that these intervals we're finding are not giving us the true amount of soup eaten. It's the amount more or less eaten since we're comparing. So if I had done ordinary minus refill, I would have gotten negatives here. And the negatives would have we would have interpreted that as the people eating from the ordinary bowls would have eaten an average of 2.2 and 10.2 ounces less than those eating from the refill bowls. Okay, let's look at a hypothesis test now. Many office coffee stations collect voluntary payments for the food consumed. Researchers at the University of Newcastle upon Tyne performed an experiment to see whether the image of eyes watching would change employee behavior. They alternated pictures of eyes looking at the viewer with pictures of flowers each week on the cupboard behind the honesty box. They measured the consumption of milk to approximate the amount of food consumed and recorded the contributions in pounds each week per liter of milk. So here we have the pound symbol, and then it's per liter, that's an L. The table summarizes the results. Do these results provide evidence that there really is a difference in honesty, even when it's only photographs of eyes that are watching? So here we're looking for evidence, so we are going to perform a hypothesis test. We're going to assume our significance level is 5% since they don't say. So my hypotheses here, we're comparing, and this time we're dealing with means, right? So we have mu, and it's going to be, let's see, we'll do mu eyes. So the mean amount of money contributed for those that had the eyes watching them, minus the mean amount of those who had the flowers behind them. The null, remember, would say there is no difference. So it would say that it equals 0, right? You can also just put mu E minus mu F, or equals mu F. Since we're looking to see if there's evidence that there's a difference, that means we're looking for mu E minus mu f doesn't equal 0, which you can also just say mu e doesn't equal mu f. So the mean amount given for the eyes is not the same as the mean amount given for the flowers. Step 2 is, of course, check your conditions. So you check to make sure that you have independent groups, the 10% condition, randomization, and also the nearly normal. And we're dealing with a small amount, small sample size, but it's over 5 weeks. So we assume that the samples given over the 5 weeks was, quite large. But it's less than 30 for n, so it's probably safe to say it's unimodal and reasonably symmetric. All right, so since my conditions are satisfied, it's okay to use a 2-sample t-test. All right, for step number 3, we have our calculations, which we're going to do y bar e minus y bar f. So if I look at my table, it's 0.417 pounds per liter minus 0.151. And when we subtract them, we get 0.266 pounds per liter. Okay, I want to find the standard error. So to do that, I'm going to take the square root of the s's. So it's going to be 0.1811 squared over 5 and 0.067 squared over 5. And we end up with 0.0864. Okay, I'm going to find t next. So my t value, and that's going to be my point estimate, and then it's minus the mean, which is from the hypothesis test, from the hypotheses, right? Your claim is 0, there is no difference. And then we're going to divide that by 0.0864. And when you do that, you get 3.08. Okay, let me shrink that a little bit. All right. Step 4, we've got our t-model. And we know here we have 5 plus 5 minus 2, so we have 8 degrees of freedom. The mean is 0. And our t value is 3.08, so I'm going to go 3.08 standard deviations in either direction. Here we've got t equals 3.08, and we're looking at that rejection region, and t equals negative 3.08, and we're looking at that rejection region. Okay, so I am trying to find the probability that t won't equal 3.08, which I can just do 2 times the probability that t is greater than 3.08. It's a two-tailed test. So I'm going to do 2 times TCDF. And on your calculator, it's going to ask you for the lower bound. So I'm going to use 3.08. The upper is going to be 100. And then I'm also doing my degrees of freedom here, which is 8. Okay, so let me pull up the calculator so you all can see here. So second vars, number 6. And I'm going to delete that. Okay, my lower bound, like I said, is 3.08, comma, my upper is 100, and my degrees of freedom here is 8. And then hit enter, and we get 0.0076. So about 0.008. And that's my p-value. So now steps 5 and 6 is our decision and then our interpretation. So since 0.008 is less than our alpha level, we're going to, of course, reject the null. And anytime you reject a null, you could say there is strong evidence, there is statistically significant evidence, to suggest what? To suggest that people leave higher average payments for food if the pictures of eyes are watching, because that's what my alternative said, right? That there is a difference in the amount left. And here it shows that there's more that's left. So to suggest people will leave a higher average amount for food if pictures of eyes are watching. Okay, there's 2 problems here for you to try. One of them is a confidence interval. The other is a hypothesis test. So I would recommend pausing the video to read the problem and then to work them out. And then you can unpause when you're ready to go over it. Should you buy generic rather than brand name batteries? A statistics student designed a study to test battery life. He wanted to know whether there was any real difference between brand name batteries and a generic brand. The table shows us data, which is time in minutes. Okay, so that's how many minutes each brand, lasted. How much longer might the generic batteries last? Construct and interpret a 95% confidence interval for the true difference between the mean lifetime of the generic batteries and the mean lifetime of the brand name batteries. Assume the assumptions and conditions have been satisfied. So here you're missing the statistics, so we're gonna have to find them. So you're gonna have to make sure you go on your calculator and you're gonna enter the data there. Okay, and to do that, remember you're gonna go into stat and then click enter. Right now I have data in there, so to delete it, I'm just gonna scroll up to L1 and hit clear, hit down, and then scroll over to the right, do the same thing for L2, hit clear, hit down, and then go back over to L1. So in L1, we'll put the brand name. So we're gonna type those in. Okay, so there's my brand name. And then over here, we have our generic. Okay, now I want to calculate statistics for it. So I'm going to go back to stat, go to calc. This time you can click on number 2, 2 variable stats, and then make sure your lists are in the correct place, and then hit enter, and you have all your stats you need. So you can see X bar, which is your sample mean battery life for the brand name, and then SX is your sample standard deviation for brand name. And then if you scroll down, you can see the sample size, which was 6. And then you've got your y's. So that's going to be for the generic. And the sample mean for that was 206. The standard deviation we're going to use is the SY, which is 10.3. And then again, n equals 6. So I'm just going to kind of make a little table here that we can look at. You've got something like brands and then generic. And we've got n, our sample mean, and our sample standard deviation. Okay, and we know that both were 6 for the sample size. Brand name had a mean battery life of 187.4 and generic was 206. And then standard deviation for brand was 14.6 and generic was 10.3. And here I'm conducting a 95% confidence interval. So how much longer might the generic batteries last? Okay, so we're gonna take here, I wanna keep it positive, so I'm gonna do y bar generic minus y bar brand. That'll give me a positive number, plus or minus my t star. And I know that my sample size is 6 for each, 6 plus 6. And then when I subtract 2, I get 10 for my degrees of freedom. Remember, that's an estimate. And then you've got your standard error. So here you're going to do S, standard deviation of the generic squared over the total sample size for generic, plus the standard deviation of the brand name squared over the sample size for a brand. And we're just going to plug in our values here. So here we would get 206 minus 187.4 plus or minus. Now I need to look up t star 10. So again, we're going to go to the t table and we're going to look under 95%, which is the second column there. And I'm going to go down to my 10 degrees of freedom. So my critical value is going to be 2.228. Okay, so I've got 2.228 times, and now I'm going to plug in 10.3 squared over 6 plus 14.6 squared over 6. And when you subtract 206 and 187.4, your point estimate is 18.6. And then when you multiply the other side, your margin of error is going to be 16.3. So my confidence interval comes out to be 2.3 and 34.9, okay, which is a wide interval. So we would interpret that as I am 95% confident that the generic batteries would last on average, right? We're dealing with averages, so it's important to say that, between 2.3 and 34.9 minutes longer than brand name batteries. So basically, I mean, if you're talking to a normal person that maybe hasn't had statistics and they're like, well, what does that mean? You're basically saying that if the generic batteries are cheaper, there seems a little reason to not use them, right? That's all this is basically saying. Okay. Second question If you bought a used camera in good condition from a friend, would you pay the same as you would if you bought the same item from a stranger? A researcher at Cornell University wanted to know how friendship might affect simple sales such as this. She randomly divided subjects into two groups and gave each group descriptions of items they might want to buy. One group was told to imagine buying from a friend whom they expected to see again. The other group was told to imagine buying from a stranger. Here are the prices they offered for a used camera in good condition. Is there a difference in the price people would offer a friend rather than a stranger? Perform a hypothesis test at a significance level of alpha equals 0.05. Okay, so we're going to, again, check our conditions really quick, right? So we've got the prices people would buy from a friend, and then prices people would buy from a stranger. We would assume that each group would have no influence on each other, so they're independent. It says the researcher randomly divided subjects into two groups, so that takes care of the randomness. We know that the sample size is less than 10% of the population. And since we have a sample that's less than 30, it's safe to assume the distribution would be unimodal and roughly symmetric. Okay, I wouldn't expect any skewness there. All right, so step one for your hypotheses, you know that you've got mu, and again, we need to figure out the sample statistics, but we'll do that shortly, okay? So here you have mu f minus mu s, so the mean amount of money you would pay to a friend minus the mean amount of money you would pay to a stranger. The null would say there's zero difference, and the alternative would say there is a difference. So it's going to be not equal to 0. Okay, we said our conditions are okay. So it's okay to use a 2-sample t-test. And for step number 3, we need to perform our calculations. So for the calculations, we don't have mu f or mu s. So what we need to do is make a little table. We've got, a friend and stranger. We know we need the sample size. We know we need the sample mean and the sample standard deviation. So you're going to enter the data in as we did in the last example, and you're going to find those statistics. Now, when you enter it in, you need to be careful because you don't have the same sample size for each. So if you try to do a 2-stat variable on it when you're calculating, it's going to come up with an error message because the calculator is trying to pair up the numbers. So you're going to have to do a 1-variable stat calculation for each of them. So in other words, when you're typing it in, after you had your list here, okay, so you're in your list, you type it all in, then you're ready to perform the calculations. When you go back to stat and go to calc, choose 1-variable stat, and you're going to have to do it for each of them. So you would have to go to 1-variable stat, and then your list is L1, and then hit enter. And then you would have to go back into stat again, and this time do 1-variable stat, but you need to change your list from L1 now to L2. So I'm going to change this to L2, and you do that by just clicking second 2, and then hit enter, and then it gives you the statistics for the second set of data for the strangers. When you do that, you're going to come up with the following. So for n, you can just count. There's 8 data points for friend. The mean was 281.9, and the standard deviation was 18.3. And then for a stranger, it's 7, 211.4, and 46.4. So those are the summary statistics that we have. Okay, so now I'm going to find y bar f minus y bar s, and that's just 281.9 minus 211.4 which is 70.5. And then the standard error of your y bar differences is going to be the square root of 18.3 squared over 8 plus 46.4 squared over 7. And when you do that, you get 18.7 for your standard error. So your t-value is going to be your point estimate minus the mean divided by the standard error. And you should end up with 3.77. So when you sketch your t-model, you know you have a t-model with 13 degrees of freedom, right? Because there's 8 in sample 1 plus 7 in sample 2. That's 15 minus 2 is 13. And the mean is going to be 0. And we're going to go 3 standard deviations in either direction. So we have 3.77 shaded to the right and negative 3.77 shaded on the left. We're trying to find the probability that t doesn't equal that. So we're going to do 2 times the probability that t is greater than 3.77, which remember I need to do 2 times TCDF. And then I've got my lower bound, which is 3.77, my upper bound, which is 100, and my degrees of freedom is 13. Okay, so I'm going to do 2 times, and then second vars, number 6.
With Boost from Kroger, enjoy unlimited free delivery. Kroger, fresh for everyone.
There we go. Okay, so it was 2. Let's do this again. So it's 2 and then times TCDF, so second vars, number 6. Okay, and my calculator always puts things in there. I don't know why it does that. So my lower bound is 3.77. My upper bound is going to be 100. And then my degrees of freedom is going to be 13, right? And then hit enter. And you get 0.0023. Okay. So now comes my decision and my interpretation. Well, since 0.0023 is less than my alpha level, we are of course going to reject the null. Okay, so there is strong evidence. Again, you can say statistically significant evidence to suggest people would not offer friends and strangers the same average amount, right? That's my alternative. That's what that's saying. Okay, for a used camera. In fact, it appears they'd offer them more, right? Based on what we looked at, $70.50 more. And that's it, folks. If you have any questions, please reach out to me. I'm happy to help you, and I hope you've enjoyed the video. Have a great day.